To assign a probability to an event, we need to define that event in a precise way. As such, we need to have a good grasp of the vocabulary associated with probability. First, an experiment is a process that, when performed, results in one and only one of possibly many outcomes. For example, if we define our experiment as record the result of one flip of a coin, only one outcome will occur out of two possibilities, heads or tails. If the experiment is defined as measure the height of the next person who walks in the door, the person walking through the door will have only one height, of possibly many heights depending on the random nature of the people who might enter the room. An event is the outcome of an experiment. I often use event and outcome interchangeably, but the idea is the same. We will ultimately want to study the probability of different events, so it's important to be able to identify the possible events that could result from an experiment. The collection of all outcomes for an experiment is called the sample space. Let's take a look at a few examples of experiments and their sample spaces. If we define an experiment as flip a coin once, the possible events that could result are head and tail. Therefore, the sample space consists of head and tail. For the experiment defined as roll of one die, the sample space consists of the faces of the die, 1, 2, 3, 4, 5, and 6. Production engineers may be worried about the tardiness of fulfilling orders, so let's define an experiment as observe the delivery of one order from the factory. Let's then define the sample space as possible outcomes, early, on time, and late. If we wanted to be more specific about the lateness of orders, we could be more granular in the definition of possible events. 1 day late, 2 days late, and so on, so long as we are specific in our sample space. Let's define another experiment as flip a coin twice. Here we have to make sure that our sample space accounts for the outcomes of two flips, head-head, tail-head, head-tail, and tail-tail. Note that we distinguish between tail-head and head-tail because we are treating the two flips separately. One last example demonstrates how large the sample space can get. Say there are two machine operators at Venn Diagrams Industries, a latex manufacturing company, and each operator can have at most 4 batches of latex at their workstations. That is, depending on how the flow of latex batches is proceeding at the factory, an operator could have 0, 1, 2, 3, or 4 batches at their station. When 2 operators are involved, the sample space contains 25 possible events when the experiment is defined as observe the number of batches at each of the 2 workstations. Were we to observe 3 operators or more, the sample space would continue to increase. We'll see later that the more things that must occur, the less likely a very specific outcome is, due to how big the sample space gets. We have a means to visualize the sample space with a Venn diagram. This diagram was conceived by John Venn, a 19th century logician whose beard was the envy of statisticians around the world. The idea behind a Venn diagram is amazingly simple but incredibly useful. A rectangle represents the entire sample space of an experiment. We then represent particular subsets of that sample space that we're interested in with circles, and we can view the overlap of different events. Let's take a look at the events A, B, C, and D. They reside within sample space S, represented by the rectangle. The size of the events indicates how many ways that the event is observed in the sample space. Here, event B occurs most often. A and B can occur simultaneously, as there is some overlap of those 2 events, or they can occur individually as part of event A does not reside within event B, and vice versa. Event C occurs only in conjunction with event B, and C lies entirely within B. Finally, event D does not have any overlap with any of the other events, suggesting that event D cannot occur simultaneously with A, B, or C. Event D is said to be mutually exclusive of A, B, and C. The easiest way to explain Venn diagrams, and later many of our probability examples, is with the tried and true illustration of a deck of 52 playing cards. Just to be sure, let's familiarize ourselves with the elements of a deck of cards. There are 4 suits: hearts, clubs, diamonds, and spades. Hearts and diamonds are red in color, while clubs and spades are black. Within each suit there are 13 cards, ranging from 1, or ace, all the way to 10, and then 3 face cards, jack, queen, and king. So, 13 cards in a suit by 4 suits is 52 cards in total. If we define an experiment as draw a card at random from the deck, we have many different events that we could define. Let's define our sample space as all of the possible events, and let's define a few events in particular. Define event A as the card we draw is a red card, and event B as the card we draw is a diamond face card, and event C as the card is an ace. Note the overlap in events. All diamond face cards are also red cards, so event B is contained entirely within A. And as half the aces are red cards, the heart and diamond aces, half of event C coincides with event A. Note that events B and C are mutually exclusive. There's no overlap with events B and C, as a draw of one card can't be a diamond face card and an ace at the same time. Here are a couple more Venn diagrams that may help illustrate things. Maybe? Okay, maybe not. Understanding events and visualizing events with Venn diagrams will help us in quantifying their likelihood and applying a few probability rules a little later on.